Bicyclic compounds are compounds that contain two fused rings, and for us to name them properly, we include the name bicyclo, right? We want to make it very obvious that it's two rings fused bicyclo to the parent name. So what we do here is that we locate where that fusion happened. We call that the bridgehead, those carbon atoms, and then we include both the position where that is happening as well as how many carbon atoms are participating in that second or that bridged ring. So here, for instance, we have bicyclo 311 heptane to describe this system, whereas the second system, the one on the right, bicyclo 221 heptane. Now let's talk a little bit about constitutional isomers. This is gonna be one of those big topics that we keep seeing throughout the rest of the course. And isomers are super common in organic chemistry. Basically, you have the same molecular formula, but you have the ability to produce a different set of structures. And when that happens, we need to be able to differentiate between them. This is super important because when your shape changes, the structure will determine the function. So your physical as well as your chemical properties may change between different types of isomers. So let's start by talking about constitutional isomers. These are structures where you have different connectivity between the atoms. We have here 1, 2, 3, 4, 5, 6 carbon atoms. Here you have the same 6 carbon atoms, but you have a little bit of branching here. These two will have the same molecular formula, but that branching actually makes it an isomer. It's important to note that as the number of carbon atoms increases, so does the number of constitutional isomers. Now this table is not for you to memorize, it's just to give you an idea of that progression, right? It's an exponential increase. We go from one constitutional isomer with one of our simplest molecular formulas, just 3 carbon atoms. As you move to 6 carbon atoms, just twice that, you went from 1 to 5 isomers. You go to 10 carbon atoms, you have 75 isomers, and so on, right? You get a 64 billion, trillion really, isomers when you have 40 carbon atoms. So the number is astounding, right? By increasing the number of carbon atoms. For us to be able to recognize different structures as either being isomers or being the same compounds. Now I want to start this out by saying I'm going to describe a method here. This is not the only method. If you have a way that works for you, then that's great. You can use that as well. This is just one way in which you can recognize whether the structure is an isomer or is an identical molecule. So, for instance, we have these two, and we're not sure if they are the same molecule or if they are isomers. So what we do is that we flip one of the molecules in 3 dimensions, and we rotate around its single bonds until it is superimposable with the other molecule. It's going to require a little bit of visualization, a little bit of imagination, and definitely a lot of practice, right? So I advise that whenever you have molecules like this across the presentation, across your textbook, just start drawing them out, try to see if you can get some isomers, see what that looks like. Once we start rotating them, if we run into a scenario where they have the same IUPAC name, then definitely they are identicals. I can tell you right now that these two are identical. For me, I can visualize them at this point because I've done this so many times. This is a 5 carbon atom parent chain. In position number 3, I have a methyl group. Here, 1, 2, 3, 4, 5 parent chain. Position number 3, methyl group. So these are not isomers. These are in fact the same structure. Right? The two sort of closed off here. 180-degree rotating along carbon 3 and 4, like the example we just saw on the previous slide, it will make it a little bit more obvious, right? So if I rotate here, then this carbon atom sort of faces this way, and it looks a lot more like this guy right here, and vice versa. Following IUPAC rules for naming, use the same name as well. This is why following the rules when we're locating parent chain, locating substituents, and all this stuff, if we all follow the same rules, we end up with the same names, so we're able to identify whether something is identical or it's a isomer. Right? Now let's talk a little bit about relative stability. We identify stability of different hydrocarbons by performing calorimetric studies. That's just a very fancy way of saying we burn them. When you burn a hydrocarbon, you generate a combustion reaction, and the product is going to be a carbon dioxide and water, stoichiometric amounts of each. Now here you have a single chain, whereas in the middle you have a little bit of branching, and then you have a whole lot of branching, right? Even more branching. So um, when you burn off or you generate a combustion reaction between these, you can see that they generate different amounts of energy. The lowest amount of energy is going to correspond to the least stable of your different compounds, and then the more energy you burn off, the more stable the system really was. Various components of all of these hydrocarbons, um, we can find them in petroleum, right? When you have crude oil, you have crude petroleum, you separate it by distillation based on the actual boiling range or boiling point range of each of the group of compounds. They have different uses, they have different densities, etc. The smaller ones, they are natural gas, petrochemicals, plastics. As you keep moving up in the number of carbon atoms in your compounds, then you have your solvents, then you have your gas, then you have your jet fuel. Eventually you end up with asphalt tar, really um, viscous thick solids, right? So that's here in the bottom. In the case of gasoline, the one that we deal with the most, it is a mixture of straight, branch, and aromatic hydrocarbons, usually between 5 and 12 carbon atoms in size. Large alkanes can be broken down into smaller molecules by a reaction known as cracking. Right? We do that, we add hydrogen, very high temperatures, very high pressure, and then those chains sort of break into uh, smaller chains. Straight chain alkanes can be converted into branched alkanes and aromatics through reactions known as reforming. After using these processes, the yield of gasoline is about 47% rather than 19%. So what that means is that once you extract all of these compounds that will eventually become the gas that we use, that we get at the pump, they undergo some chemical processes before we actually use them, such as cracking and reforming. Now let's talk a little bit about Newman projections. These projections refer to ways in which we can see uh, alkanes, right? So we can sort of talk a little bit about the rotation within single bonds in a given molecule. So in this case, we talk about single bonds, how they rotate, resulting in multiple three-dimensional shapes. We're going to call them conformations. There are various ways to represent the three-dimensionality of those shapes in a compound. We have three examples right here. We have the wedge and the dash. This one you're a little bit more familiar with. We've seen them in our previous chapters. We also have the sawhorse conformation. This one is not as common, but you can still see it around. And lastly, the Newman projection. This one we're going to be seeing a lot more of it because it tends to be a little bit more summarized, more compact, a little bit more elegant, if you ask me. And it gives you the same, if not more, information than your wedge and dash conformation. Newman projections are ideal for comparing the relative stability of possible conformations resulting from single bond rotation. A Newman projection is a perspective, right? We look straight down a particular carbon-carbon bond. Doesn't have to be any specific one, so long as we are indicating which ones we're using. You can see the observer is looking through here. So for the observer, the hydrogen atoms in red are closer, the hydrogen atoms in blue are a little bit further away. So we say that this dot right here, that turns into sort of an upside down Y, that's the carbon in the front, and then the circle will be the carbon in the back. And then we sort of write down the substituents associated with those two carbon atoms. In this case, the substituents are all hydrogen atoms. They may be something else, whatever it is in a specific case. Now, it doesn't have to be hydrogen. In an example here, we actually have things other than hydrogen. The observer is looking through these two carbon atoms. And again, it doesn't have to be those two. We just happen to choose those two for the example, right? So long as we indicate which carbon atoms we're choosing, we're okay. So anyways, in the case of the observer, this is the carbon atom in the front, this is the carbon atom in the back. In the front, you have bromine. To the observer's right, to the observer's left, you would have hydrogen, and to the bottom or down, you would have a methyl group. So straight down, to the right, to the left. And in that case, because we have sort of an alternated structure in the back, then bromine will be to the bottom right, methyl will be to the top, and it's not really indicated here. I would assume hydrogen to the bottom left or whatever we should have here. And that's basically it. That's the basis of Newman projections. This is not particularly, I wouldn't say it's complicated, but I would say that it does require some practice to become more used to it. The angle between atoms on adjacent carbons is called a dihedral angle. The dihedral angle in an alternating structure like the one we have here is 60 degrees. When we have that type of angle, that is the lowest in energy, it's the most stable, simply because the atoms are not in front of each other, which we would call an eclipse conformation. So there's no, or there's a lower energy of repulsion between the electrons in this case, in the hydrogen atoms. Staggered conformations are more stable than eclipsed. So eclipsed, they're literally eclipsing each other. So technically we wouldn't be able to see the hydrogens in the back, so we draw them sort of like this so that you can still see them, but we're sort of showing that they are one behind the other, right? That's what we call an eclipse conformation. The difference in energy between these conformations is due to what we call torsional strain, and in this specific case that energy equals to 12 kilojoules per mole, so it's quite significant. As you can see, when your molecule is rotating, you go between your staggered or your alternated to your eclipse, and so on and so forth. The energy goes up and down. Right, so this is the energy profile of your ethane molecule whenever it's rotating. It's possible the eclipse conformation is 12 kilojoules per mole less stable because of electron pair repulsion between the eclipsing bonds. So 3 bonds, about 4 kilojoules apiece, so that will be 12 kilojoules per mole. With a difference of 12 kilojoules per mole in stability, at room temperature, 99% of the molecules will be in staggered conformation. So I expect very few, if any, to be in eclipse conformation. The difference in energy can also be rationalized by the presence of stabilizing interactions in the staggered conformation. What does that mean? It means that a field bonding molecular orbital has side-on-side overlap with an empty bonding. So you have a little bit more room. Those molecular orbitals that have electrons, they have more room to just spread out, lower its energy. And when you go from that into an eclipse position where you have less room, your energy has to go up, right? Because your electrons are getting squished back into a smaller volume. The analysis of torsional strain for propane, when we move from ethane to propane, is very similar. What changes is the magnitude. We went from 12 to 14 kilojoules per mole, so even bigger amount of energy. That's because methyl is much larger than hydrogen. The barrier of rotation for propane is 14 kilojoules per mole, which is, as you know, 2 kilojoules per mole more than ethane. For butane, we see the same thing. However, we see a little bit more variety, because when your methyl groups are actually finding each other, then you get a maximum of 19 kilojoules per mole increase in energy. Every other time you have only 16 kilojoules per mole. That will be the torsional strain. The stability of the different staggered conformations differ by 3.8 kilojoules per mole. When the methyl groups are gauge to one another, in other words, 60 degrees, and that dihedral angle between the methyl groups, these are what we call the gauge conformations. This will be the anti-conformation. So this will be where they are the least stable, and then the most stable is the one on the left. The highest energy conformation for butane results when the methyl groups eclipse one another. Each methyl group eclipsing interaction accounts for 11 kilojoules per mole of energy.